James Webb Telescope's unexpected new discovery has left scientists speechless. The James Webb Space Telescope is capable of much more than merely taking beautiful photographs of the sky. The observatory has solid evidence of the presence of carbon dioxide in the atmosphere of a planet outside our solar system. The JWST discovered this gas on a gas giant, WASP 39b, at a distance of 700 light-years. This discovery gives vital information about the planet's chemistry. This discovery also proves the JWST's ability to detect and measure carbon dioxide in the thinner atmospheres of tiny rocky planets, and was approved for the publication in the Nature magazine. Carbon dioxide has never been detected on an exoplanet. However, specialists believe that the gas could help them grasp the evolution and formation history of exoplanets. Before we explain this JWST's recent discovery, let us review some of WASP 39b's qualities. So brace up, because this journey into space will be intriguing. WASP 39b is a hot gas giant planet with a diameter 1.3 times that of Jupiter and a mass around 1/4 that of Jupiter, roughly the same as Saturn. Its high temperature of 1600 degrees Fahrenheit leads to some of its severe puffiness. In contrast to the colder, more dense gas giants in our solar system, WASP 39b orbits its star very closely, just about 1/8 the distance between the Sun and Mercury, completing one complete cycle in about 4 Earth days. According to reports, the planet was discovered in 2011 based on ground-based observations of a minor, recurrent dimming of its parent star. WASP 39's light when the WASP 39b traverses or travels in front of the star. WASP 39 is a star that is smaller and less massive than the Sun. Due to its very close proximity to its star, WASP 39b is incredibly hot and is possibly tidally locked, with one side always facing the WASP 39. To investigate planetary atmospheres, researchers can use transiting exoplanets like WASP 39b, whose orbits we see from the edge rather than from above. Some of the starlights are partially blocked by the WASP 39b during transit, resulting in overall darkness, and some are reflected by the planet's atmosphere. Because different gases absorb different combinations of colors, researchers can determine the specific composition of an atmosphere by measuring minute differences in the intensity of light transmitted over a wavelength range. Because of its inflated atmosphere and regular transits, WASP 39b is an ideal target for transmission spectroscopy. The Hubble and Spitzer space telescopes earlier discovered water vapor, sodium, and potassium in the WASP 39b's atmosphere. JWST, on the other hand, has been able to identify the carbon dioxide signal due to its more potent and sensitive infrared capabilities. The discovery was made with the help of JWST's near-infrared spectrograph, a very sensitive spectrograph that divides light rays into barcode-like spectra that depict how the compounds under study absorb light. As seen in a sequence of light curves from Webb's near-infrared spectrograph, the intensity of 3 distinct wavelengths of colors of light from the WASP 39 star system fluctuated over time as the exoplanet passed in front of the star on July 10, 2022. When an orbiting planet passes in front of a star and a telescope, it partially blocks some of the star's light. The NIR-SPEC Prism Bright Object Time Series mode was used to achieve these findings, which included using a prism to disperse the light from the WASP 39 and monitoring the brightness of each wavelength and predetermined time intervals. The JWST spent more than 8 hours observing the WASP 39 star. It began 3 hours before the transit started and ended 2 hours after the end of the transit. The actual transit lasted roughly 3 hours. Each of the curves shown below has 500 distinct brightness measurements, or about 1 every minute. Although the planet partially obscures all colors, some are more obscure than others. This obscurity is due to the varying amounts of wavelengths that each gas in the atmosphere absorbs. As a result, each color's light curve is slightly different. A little hill between 4.1 and 4.6 microns in the resulting spectrum of the WASP 39b's atmosphere provides the first definite, in-depth proof of carbon dioxide ever identified in an extrasolar planet. Because carbon dioxide absorbs light with a wavelength of 4.3 microns during the transit of WASP 39b, it is less intense than light with a wavelength of 3.0 or 4.7 microns. The massive carbon dioxide feature grabbed me as soon as the data arrived on my screen, according to a member of the JWST Transiting Exoplanet Community early release science team that carried out this research. Crossing a critical threshold in the study of exoplanets was a momentous occasion. No other observatory has before documented such minute fluctuations in the brightness of so many distinct colors in an exoplanet transmission spectrum spanning the wavelengths ranging from 3 to 5.5 microns. Instead of taking direct images of the exoplanet or its atmosphere, with the JWST or any other existing telescope, researchers compare measurements of the star's regular light to light seen through the exoplanet's atmosphere when it passes in front of it. Having access to this part of the spectrum is required to assess the abundance of gases such as water, methane, and carbon dioxide, which are thought to exist in a wide range of exoplanets. Natalie Batalla, the team's leader, noted that discovering such a strong carbon dioxide signal on WASP 39b is hopeful for the discovery of atmospheres on small-sized planets. Understanding the composition of a planet's atmosphere is critical because it provides insight into the formation and evolutionary history of exoplanets. Carbon dioxide can be used to measure the total carbon and oxygen component of the atmosphere, which is particularly sensitive to the conditions in the disk where the planet formed, making it a vital tracer of the history of planet formation. Scientists can use the carbon dioxide estimate, for example, to better define the planet's original formation site, the properties of the excreted solids and gas, and the planet's subsequent migratory history. By researching this carbon dioxide feature, we can estimate the amount of solid and gaseous material used to create this WASP 39b. JWST will make this measurement for many planets during the next 10 years, providing knowledge on the specifics of the planet formation as well as the quirks of our solar system. The James Webb Space Telescope is the world's most advanced space research observatory. The WASP 39b NIR-SPEC PRISM observations are part of a larger inquiry that includes observing the planet using multiple JWST equipment and examining 2 other transiting planets. The study is part of the JWST Early Release Science Program, created to discover data for the exoplanet research community as soon as possible. This study will enable scientists across the world to be trained on how to interpret these new data types and be prepared to take advantage of the JWST observations in the future years. According to Natasha Batalha, NASA's open science guiding principles are focused on early release science initiative, fostering an inclusive, transparent, and collaborative scientific approach. And on that note, we have come to the end of this video. Let us know in the comments section what you think is the origin of these lights, and if you think this is enough proof for extraterrestrial civilization. Don't forget to give this video a thumbs up, smash the subscribe button, and turn on the notification bell to get notified when we post a new video.